Welcome to the Niagara College fiber laser system. This fiber laser has been constructed in the college itself using a whole bunch of components that were laying around. It's pretty standard of a fiber laser. It is a ring laser configuration, but it is a unidirectional ring, meaning that it only lasers in one direction, not both. In other words, the actual fiber amplifier has an input and an output. Now you can see the output of the amplifier right here, or sorry, the output of the laser itself. If I run a single trace, you'll notice it's at 1530 nanometers. That's what the grating filter is set for. And if I set it for, let's say, 1540, and I run another trace, you'll notice that the laser is completely tunable, well, over a certain range at least. The EDFA, as you probably well know by now, has a very wide range. It can amplify over about 60 nanometers. And so the actual output of this laser is also tunable over about 60 nanometers. Now the laser itself is a fairly simple beast. This is the output from the amplifier. It goes into an, well, let's call it output coupler. It's actually a splitter, and we use it as an output coupler. Part of the output ends up right here, and it goes into the OSA. The other part of the output goes into the fiber grating filter, which then selects the wavelength, and that acts as your feedback loop going back to the input of the actual amplifier. So really, it's a fairly simple beast. You have an output, you take off about a half, that's your actual output. The other half goes through a feedback system, which is wavelength selective, and then goes back to the input of the actual amplifier itself. So let's take a look at each component as we go along. A couple things we're going to have to do today to take a complete analysis of this system. One of the first things we're going to have to do is characterize this amplifier. Yeah, it is an EDFA from Nortel, a very cool amplifier by all stretches. It has an input, it has an output, it's double pumped, meaning that the actual length of the fiber is pumped from both ends. That's a much better way to go than most cheaper fiber amplifiers. It ends up making a very, very high gain amplifier. The gain of these things is around 30 some odd dB. So that's over a factor of 1,000. But it also has a saturation factor. And you remember Psat from lasers. That's one of the things we have to determine from this. In theory, we can calculate it. In reality, that never really works. The easiest way to do it for a fiber like this, a fiber amplifier, is to actually measure it. So that's where we're going to start, by measuring the actual amplifier's characteristics, the Psat characteristics. So I'm going to rewire the system, and we'll take a look at those characteristics. Okay, the first step to measuring this thing is to start off with a source. What I'm going to do is I'm going to use a laser source. It's a stabilized laser, one of those communications ones. It says 1545 nanometers. So what I've done is I've wired the output of this directly to our OSA, and this way we can measure the outputs. You'll notice on there, this is the graph over here, of course, on the OSA. And what I'm going to do is I'm going to zoom in on that graph so you can see what it actually looks like. All right, let me just get this out of the way. If I set the span a little bit wider, say 50 nanometers, okay, we'll take a scan there. Notice all those modes appearing. Those are the modes of the laser diode as expected. They're spaced by, that's the FSR, of course, the spacing of those modes. And that's set by the length of the laser diode and the index of refraction of that specific diode. As I start zooming into this thing, okay, I'm going to use a 5 nanometer span from one end to the other. You can see the individual modes. And what I'm going to do is, okay, there's the actual center mode right there. That's the one we're going to use in order to measure the actual amplifier's characteristics. We have to use some wavelength or some frequency. I'm going to use this one. And it's at 1.54615 nanometers. That's the dead center mode right there. And it's at negative 10.03 dBm. Okay, so negative 10.03 dBm. In other words, if I feed this thing in directly to the amplifier, I'm going to get negative 10 going in. Okay, so let's reconfigure this thing so we can measure this amplifier now. Okay, at this point I'm wiring it up so that I can actually simply go from my diode directly into this amplifier. The output from the amp is going to go directly to the OSA. So, a couple little tricks to doing this. Number one, this thing has the world's absolute worst input and output connectors. They're hidden behind this little panel over here. I've had to change them because this one has an APC on this end and the other one on the other end. Okay, so I'm going to change that over, and I'm going to use the normal flat connectors on this one, and I'm just going to connect this up right here to the input of this thing. You'll notice the amplifier is off right now. Little door, as soon as you open it up, automatically shuts off. So it is an interlock system. That's rather typical. I close it up. There we go. Now I've got an input coming from here. So the diode goes directly into the amplifier. The output from the amplifier, okay, hopefully I can just move some of these cables out of the way. The output from the amplifier goes directly to the OSA. Well, not directly. Part of the problem with the output of this, it's rated at plus 17 dBm. That's 50 milliwatts. I don't know what the input of this thing is going to take, but it sure as hell isn't even close to that. In other words, you're going to burn it up. So what I have to do is cut it down. The easy way to cut these things down is to use an attenuator. That is a fiber attenuator right there. This is a 15 dB attenuator. So what I've done is I've taken the output from this amplifier on this cable over here, and I put a 15 dB attenuator. So everything you read on here will be 15 dB higher on the output here than what you actually read on here. Which means when this amplifier produces plus 17 dBm, you'll actually read it as plus 2 dBm on here, and you won't blow up the OSA. Very, very important that you always do those type of things. All right. Well, right now when I read it, I've got the input going in over here. All right, so there's my diode. Diode input goes into here, comes out, goes through this, and I'm getting an output of 1.27, looks like. Same frequency, obviously, or same wavelength, so no change there. But look at the output. It's 1.3 plus 1.3 dBm. So what's the actual output? Well, it's not actually 1.3. As I said, there's a 15 dB attenuator. Right here, it's 1.3 plus 15. So it's actually 16.3 dBms. So that's what's coming out here, 16 dBms. Okay, what's going in? Negative 10. Negative 10 goes in, plus 16 comes out, total gain, positive 16 plus 10 point whatever it was, and that's 26 dBs of actual gain, not dBms, dBs. Gain is measured in dBs, actual power is measured in dBms. So I have a gain of 26 dBs right now. That's actually, believe it or not, a saturated gain. The gain of this thing is actually an awful lot higher than that. The problem here is I'm putting in so much power. I mean, you may not consider negative 10 dBm as being a high power, but it is for this amplifier. Because the gain is so high on this amplifier, negative 10 goes in, and we're really, really saturating that amplifier. So we're getting 26 dBms coming out, or sorry, 26 dBs of amplification over here. So I'm getting plus 16 coming out over here. And again, now you see the reason for that optical input. All right, so the gain right now I'm measuring is a fully saturated gain. Wonderful. Now you know with an amplifier that the thing actually, the amount of gain that you get depends on the input. In other words, right now, because the input's fairly high, I'm getting a low gain. If I want to see a higher gain, in other words, I want G naught, for example, small signal gain, I have to put in a much smaller input signal. So let's measure small signal gain. Easy enough to do. I need a way smaller input signal. So what I'm going to do is I'm going to take this input over here from the actual laser, and I'm going to cut it down. I'm going to cut it down by using these attenuators. So I'm going to screw one of these 15, this one says 15 on it, all right? So I'm going to put this down. Now remember, the diode had negative 10 coming out. So if I have negative 10 here, I cut it down by 15, I have negative 25 going in. So let's put that in there, all right? And make sure everything locks properly. Okay, if I have negative 10 coming out, minus 15, I have minus 25 going into the amplifier right now. So minus 25 is going in. What's coming out? The OSA says negative 5.05, but that's being cut down by 15. So add 15 to that. All right, so you got negative 5 plus 15. You got plus 10 coming out. I got plus 10 over here, right there. All right, and I have negative 25 going in here. So I got 25 in. And what does that mean for gain? I'm getting about 35 dBs of gain. 35. That's a very, very high gain. And that's probably closer to a small signal gain. Or is it? Well, the only way to find out is to put another one of these things in. So what I'm going to do now is I'm going to add yet another attenuator into the signal to attenuate it even further. So I'm looking through my little box here. I've got a little box inside. And I'm finding all these odd attenuators. I got negative 9. There's another 15. All right. So let's take this out. There we go. Put one more of these on. And now I've got two 15 dB attenuators on this thing. All right. There we go. We'll run our trace again. Very, very low output now, as expected. So, negative 10, minus 15, minus 15, okay, so that's minus 30. So I have negative 40 dBm going in, negative 40 going in. On the other side, it says here I've got negative 19 coming out, but of course that's being cut down by 15. So add 15 to that, and it's got roughly negative 4. So I've got negative 4 coming out. I've got negative 40 going in. 40 minus 4 gives me a total gain of 36 dBs. 36 dBs. That's an awfully, awfully high gain. Well, the rest of this is done about the same way. What you do to measure this thing basically is you keep cutting down the power here coming into the amplifier, and you use various combinations. So I have a whole handful of these things, and just to show you. Okay, there's a handful of these things. You basically screw them in line over here and make a whole bunch of different combinations. And then you graph them. So you graph the input power over here, and you graph the output power over here, put them into a table, and then what you'll do is you calculate gain on each one. What you'll find is at the very, very beginning of the curve, it kind of looks like a little lump. And then it levels off. That lump at the very beginning is caused by noise. You're not actually measuring entirely the gain of the amplifier. The problem is when you get way down on this, you're actually measuring spontaneous output from the amplifier. I mean, even if I didn't bother putting any input in, let's assume just for a minute I totally disconnect this thing. All right? So there's absolutely no input. I still get an output. Negative 29 it says. That's pure noise. So the problem is when you have very, very, very small inputs to this amplifier, you're getting out almost as much noise as your signal. In other words, your noise to signal ratio is a little bit high. Yes, that's right, noise to signal, not signal to noise. You can't do that, okay? So what you have to do is graph this thing at the very, very beginning where you have extremely low powers going in. You're going to get a false sense of how high the gain actually is. It's going to be somewhere around 36, 37 dBs. It's not really that high. It's just the way you're measuring it. And then all of a sudden you're going to find the curve kind of levels off. And that's going to be G0. So what you do is you draw a line there. Usually you do this on Excel. You draw a flat line on it more or less where the area doesn't change. And that's going to be your G0 or your small signal gain. Great. Now as I start increasing the input power by taking some of these off, all right, and increasing this thing, obviously the gain goes down. And at some point that gain is going to go down 3 dB lower than G0. 3 dB lower means half the gain you started with. And if the gain that you started with was, say, this, and all of a sudden you're down 3 dB, that is going to occur when Psat exists within this thing. So now we know our saturation power. Normally we would have gone for input power and said that's the power of the input saturate. In reality, because of the way we're doing this experiment, and you'll notice there's some notes that go along with this thing, we're actually using the output power as the saturated power. Part of the reason we're doing this is because the gain is so very, very high. If you think there's about at least 8 meters of fiber wound up inside this amplifier, the power at the very beginning is very, very low. The power at the end is very, very high, about 1,000 or 2,000 times higher than it is to start with. And so it's really, really difficult, if you will, to come up with what is Psat. We use the output power on this thing. So basically, that's the way in which you characterize the Psat and G0 both of this thing. All right? And results will be provided in the lab. Well, the next thing to measure is the loop loss. In other words, all the stuff that's inside the laser. So we know what the amplifier is now. We know Psat, we know G0. What about the other stuff? Well, first off, there's going to be an output coupler. And the output coupler, I said, is 3. It's not really 3 dB exactly. This is the spec sheet for it. You could just as easily measure it. All right? This is directly from the JDS Uniphase company that made this thing. And it says here, insertion loss common to port 1, common to port 2, 1550 we use. The loss to port 1 is 3.35 dB. The loss to port 2 is 3.25 dB. And therefore, the total excess loss is 0.29 dB. So this thing has a grand total loss of 0.29 dB. That's just wasted, never to be seen again. And it's splitting approximately 40 some odd % of the signal to port 1 and 40 some odd % to port number 2. Again, these can be converted into linear numbers easily enough. So that explains that one. And the final thing is this little guy over here, the optical tunable grating filter. All right? It is completely programmable, of course. It also has a fairly high loss, unfortunately. What we're going to do once again is use our diode laser over here to measure the loss of this. And it's very simple to do. I take the output from the diode, and we know what it is because we already measured it. And I'm just going to lock that in there. So this will be our input. And then I'm going to take the output from this little guy over here. There we go. And put it over here. And I hit go. And what do I get? Bugger all. Of course I get bugger all. Here's the point. Guys, it's a tunable grating filter, right? You have to tune the grating to exactly that one peak that you remember over there. In other words, I now have to actually set this filter to be exactly that. Now it should be very simple in theory. 1.5461. 15461. All right? And we hit go again, and it should work. Problem. You notice that peak is bigger than that one. Yes, ladies and gentlemen, one of these things is off. Something's crooked, the table or the soup. Either that one's wrong or that one's wrong. What made us think just for a minute that something was going to be absolutely perfectly calibrated? You had to have expected that it wasn't going to be. So here's the deal. You now have to take this filter and slowly tune it until you get the absolute largest peak at 1.5461, which is the biggest peak coming out of this, the biggest mode coming out of that. I know it sounds like a tedious thing, but again, unless everything is 100% perfectly calibrated, it's not going to happen. And no surprises with this equipment. I mean, look at it. It's a very old OSA. We haven't calibrated in about a bazillion years, so it's not necessarily, I guess you couldn't have expected it to. So I'm going to hit repeat on this, and you'll notice where the thing is. And I'm going to go up 1 nanometer at a time and see if that helps. Oh, there we go. And we're getting closer to our peak over there. And now I'm going to go up to 148. And I'm way too far, so let's go back to where we had the largest. All right. And then I'm going to go up 0.1 nanometers. See if that gets any larger. Nope, it's getting smaller. So I'm going to go down. Yes, it's a little game that we're playing here. All right, so it's getting larger. Let's try again. No. There we go. Okay, it's getting a little bigger. No, now it's getting smaller. So I'm definitely going the wrong way. We'll try that one. All right, 14.5 it says. Now I'm going to take it up 0.01 nanometers at a time until that becomes the largest signal. So it's negative 14.2, which is larger than negative 14.5, 14.0, and I'll just keep going a little larger. 14.02 we're at, negative 14.02 I should say. Okay, negative 13.9, so keep going, we're not there yet. 13.98. Negative 14. In other words, the loss just got bigger. So I've already bypassed that peak. I shifted this thing over too far. So let me go back to where I had the largest peak. Negative 13.95. That's the largest signal I can get transferred through this, okay, at that exact wavelength. So negative 13.91 says right now. We know this was putting out negative 10. I'm getting negative 13 over here, and by the way, I removed the attenuator. It's just not necessary, of course, with these low power levels. In fact, you really don't want one there. You'd probably increase your noise and things like that. So you want to make sure the biggest signal you're measuring. So negative 13.95, and that means approximately a 4 dB loss out of this. Okay? So I've got negative 10 going in. I've got almost negative 14 coming out. I've got a 4 dB loss. And by the way, just in case you were wondering how much of an error I have here, in terms of the wavelengths, I mean, it's logical to ask. 1.5461, so 1546.1 nanometers. This is 1546.95. It looks like the error is about 0.85 nanometers between these two. Not great, but certainly not as bad as I would have thought. So now we know the loss of this is about negative 3.2 or 3.3 dB. We know the loss of this is about negative 4 dB. That's the loop itself. That's the actual loop loss, if you will, inside the actual the feedback loop of the laser. All right. And now I'm going to wire the laser back up, and we'll see what happens. We'll see what the output actually looks like. Once again, I have to change the connector on this thing. So what I'm going to do is open up my amplifier over here. I'm going to take the output directly. The only reason I have to change these connectors, again, these are APCs on here, and they're flat on the other end. So I'm going to take the output from this and wire it directly into the input of this amplifier over here. All right, so I've got the laser wired up, and I changed the batteries in the camera while I was at it. Here's the laser itself. I had to again change the connectors, so I've got the input of the amplifier coming directly from this optical grating filter. Again, APC cable on this end, flat on the other end. The output goes to the common terminal of this splitter. Port number 1 is the output from that, so it's a 3.35 dB loss. I was careful to put a 15 dB attenuator in here because I'm anticipating the output from this laser is going to go well above what this poor little OSA will handle. The other line from the splitter over here, of course, again 3.25 dB loss in here, goes into this, which we measure at roughly 4 dB loss. And there you go. That's all there is to this ring laser. I'll close this up, let the amplifier start back up, and all right, there's the output from the amplifier right now. So the amplifier, the actual laser itself is now working. It says the output is negative 0.62 dBm. Once again, add 15 to that, so it's actually about 14.4 dBm, actual positive 14.4 coming out of this. And that's at that maximum, if you will, or I shouldn't say the maximum number, but this is where we actually measured everything from. So the logical thing to do is to use this power output to model the laser at this point. Now, while we have it working, let's just show you what the range of this thing is. What I'm going to do is I'm going to take this up to 0. So this is at 147 nanometers. And I'm going to take it up to 157 just to show you what it is. All right, I've got to change the span on this thing, of course. So what I'll do is I'll change that. There we go. Not enough yet, right? No, of course not. Let's see what that. There's the output right there, so I'll just move it down a little bit more. All right. So there's the output from our laser right there at 1557. All right, let's bring this up to 1567. Still working. 1569, and let's see, what's this thing go up to? 1575. And I'm going to take this and move the center just a little bit down. Okay, so I'll push it that way on the graph. And we'll see what it looks like there. Oops. Do it on repeat. Oh, it's still oscillating. I would like to be able to take it higher than 1575, but take a look. That's as high as this thing actually goes. So the actual tuning range tops out at above 1575. Let's see how low we can go. I'm going to take this back to 1545, and we'll see what happens there. All right, there it is right there. It's still operating. We'll try 1535, and for that I'm going to have to take the center of this thing, okay, and change it. So we'll try that. Still operating. Okay, so that's 40 nanometers range already. Let's try this, 1525. It's still oscillating. That's over 50 nanometers of range. And I'm going to take this thing, put the center down a little bit. All right, let's see what happens there. And it's still going. All right, let's try again. And nothing. The laser has now crapped out. So let's take this up a little bit at a time until we start seeing it appear. Ah, okay. Now this is 1507. Take a look at that little itty-bitty glitch right there. That is actually the laser trying to oscillate. Now, if you're wondering why it's having a hard time working, well, take a look at the actual output. This is literally the spontaneous output from the EDFA amplifier at this point. And the actual gain is logically going to be considerably higher somewhere over here than it is over here. So the gain of the amplifiers is very, very low at this point, and the poor thing's struggling to operate. What I'll do is I'll increase it a little bit. This is 1508. You'll notice it's getting a little bit bigger. 1509. 1510. 1511, and clearly it's oscillating now. You notice the difference that 1 nanometer makes. It goes from barely being anything at all, and well below what I'm going to call the noise floor of the actual system, to clearly oscillating. So at this point we're clearly oscillating at 1511 nanometers. You'll remember before it went all the way up to 1575 and beyond. So we have well over 60 nanometers of range on this laser. It is a fairly wide tunable laser. Erbium has a fairly wide tuning range, of course. Its gain stretches across a very, very large range. And again, if you turn off the actual loop itself, and I can just do this by setting it very, very low, so it's doing nothing. The curve that you see over here, that is the spontaneous output curve of itself. There is no laser occurring there at all. That is just purely noise occurring. But a heck of a lot more noise occurs here than anywhere else, so logically most of the atoms want to emit at that range. We've got more energy bands available there, and you're just going to get a higher gain from this laser there. And that's about all there is for a laser like this. So there you go. There's the quick and dirty introduction to a fiber tunable laser. As I said, this one's built out of an EDFA. In reality, you could build it out of a lot of things. The EDFA itself, as I said, was a unidirectional. And one of the important things about this particular laser, it is unidirectional. There's a big spool of fiber in here. It's pumped from both ends to give you a very high gain. And there is what's called a Faraday rotator, or a non-reciprocal rotator, located on the input side and on the output side of this thing. So you only got one input and you only have one output. You can't reverse this thing. A normal laser amplifier doesn't care which way light goes. If light goes this way or light goes this way, it works the same way regardless. It just doesn't matter. This one cares. Light can only go one way in and one way out. They do that to protect these amplifiers, of course, so that you can't get an output from this thing going back into your input and potentially causing damage on things. But in reality, what it does is it makes a single loop. There are no modes, of course, you've probably noticed as well in this thing, even if you went broadband on this. If you take this out completely, and I've done this before, if you take this out completely and you simply wire the input from here directly to the output, so you have no frequency sensitive elements, you don't get modes on here, you simply get one major output mode and that's it. You don't get all those little modes like you get from a diode or from a YAG laser or anything like that, because it's not a standing wave laser. It is a ring laser. One of the claims to fame about a ring laser is that you don't get modes at all. There's no such thing as FSR, there's no such thing as modes, they just don't exist. In this case, of course, when you wire it up without a frequency sensitive element, you're just going to get the maximum output from the laser wherever the maximum gain happens to be on here. It's naturally going to drift to that wavelength. Alright, well I hope you enjoyed this tour of the laser. Data itself will be provided in the form of charts and such to match this laser so that you can do a model on this laser as well.